So, what did you guys decide on this? So instead of having $1 million, you'd rather take the penny?
Yeah.
Well, here we can see, starting off with that penny, 1 cent, 2 cents, 4 cents. Looking at this, you definitely would probably want to go with the.
Oh wait.
You probably want to go with the $1 million up front, right? And here we can see at day 14, only at $81. It started off really small, right? 8 cents, 16 cents, 32 cents. However, at day 30, we are at over $5 million.
A story like this would be great, right?
So definitely if somebody comes by and says, you want $1 million right now, or a penny doubled every day for the next 30 days, you know what to say. Well, this is an example of an exponential growth. As far as you can see that it started off growing at a very small, increasing at a very small rate. Not much of a difference between that 1 cent, 2 cents, 4 cents. But as it progresses, pretty much the 15, 20 day or so, we can see it increasing at a much dramatic, a steeper increase. As you always heard before, something growing at an exponential rate. That's what it is, as far as starting off very small and then all of a sudden increasing at a very large accelerated rate. So, our exponential functions. Definition of the exponential function. The exponential function f with base a denoted by f of x equals a to the x, where my a is greater than 0 but not equal to 1. And x is just any real number. We've seen this stuff before, in particular when we looked at graphing these, or looking at our parent functions. But my exponential growth, again, here we have the base a, but now that variable is in the power instead of being at the base. So if we want to evaluate some of this stuff using a calculator, we have our exponential function f of x equals a to the x, and we want to evaluate it at phi. What do we get? Everybody should be doing this. Some of you. No, you get 8 to the pi. I don't know why. All right, 687.291. What about this one? Here we have what do we line up with this? Sorry? Figure out to how many or decimal places your calculator say are at least 4. So here we come up with a smaller number, y. All those answers, so because of the negative, here's the one that's like a square root. You got what? 2.8. 2.8, so 8 to the negative 1/2. We have our 8. Coming up with that 0.353553. You got the negative in there, or Good to go? And for our 0.8 raised to the negative 2.5, 1.4, 1.74. Okay. Oh, 7.4. That's what you keep on saying. Same thing. No. I will not say the same thing when it comes to test time, right? So 1.7470 and so forth. Difficult stuff, I know.
Yeah.
The nice thing about our exponential functions, if you guys remember from the graphs 4 or 5 weeks ago, when we took a look at our parent functions, this was my graph of my exponential function f of x equals a to the x. The one on the right. Because here we got a negative with the x, so it's going to be a reflection about the y-axis. So either one of these graphs we look at, and they pass that horizontal line test. Horizontal line test testing for? Testing for? Right in front of you guys. Testing for 1-to-1. 1-to-1, as we learned before, especially when it comes to graphs, that it has an inverse. But another nice thing with our 1-to-1 property we can use to solve our exponential equations is for a greater than 0 and not equal to 1, a to the x equaling a to the y happens if and only if x equals y. So in other words, if I have the same base and I know they're equal to each other, all I have to do is compare the powers. So the powers equal to each other. So here I'm solving for x. 25 equals 5 to the x minus 1. Do they have the same base? Can I simplify them where they do have the same base? How so?
5 squared.
Absolutely. Rewrite 25, as I said, to 5 squared. Now I have the same base, so due to the 1-to-1 property, I ignored my 5s, I ignore my base, and I just have 2 equals x minus 1, or x equals. We can easily check that answer too. Take that x equals 3, 5 to the 3 minus 1, 5 squared, which is 25. That took us all the 5 seconds to check that. If you have the time, folks, check it. Does my answer make sense? Perhaps we put in a negative instead of a positive in our haste. So checking your work will save you some headaches there. Part B, 16 equals 2 to the x plus 2. What do I want to do here?
2 to the 4th.
2 to the 4th. Again, due to the 1-1 property, I just set the exponents equal. X equals 2. Difficult. One to the third, or actually 1/3 raised to the x power equaling 81. Definitely not the same base. What can I do? Can true to a fraction. That's why I said, if we remember the one property, what is x to the negative 1? That's the same thing as 1 over x. That's what a negative exponent does, right? So why I said we can rewrite my 1/3 as 3 to the negative 1. All right, that's the same thing as 1/3. What does a power rule say? Power rule saying when I raise a power to a power, what do I do to my exponents? We multiply. Don't forget when you have a situation like, well, this one is pretty simple, right? So negative 1 times x, so 3 to the negative x. 81 is
3 to the 4.
so we get a negative x is equal to 4 or x is equal to. And lastly, we have 2 to the x minus 2 equaling 1 over 32. To the what power? Well, 2 to the 5th gives me 32. And that negative gives me that 1 over. So 2 to the negative 5th. So again, since I have the same base, just set the powers equal. X minus 2 equals a negative 5. That's one. How do we get to the negative 5th?
Just plug in, find whatever you need.
Plug in, find whatever you need.
There.
So here we have right, 2 to the 5th is 32, right? 2, 4, 8, 16, 32, right? So then having to bring the 2 to the top, the numerator, again, that's the same thing with that negative exponent. It brings my denominator to the numerator or the numerator to my denominator. So that would be the same thing as saying 2 to the negative 5th. So here we come up with x minus 2 equals negative 5 or x equals questions on it. So I think most of it is review. There's a certain base that we've used, or that's used in nature quite a bit, instead of just using 2 or 7 or 1/2. A wonderful E. Right? 2.718 and so forth. That irrational number. The number is called R. Okay, how'd you come up with that? Why is it that number? It occurs in nature quite a bit. I'll come up with some examples for you tomorrow if you really want, or on Monday. It is a occurring number out in nature. It isn't just one that we said, hey, mathematicians got together and said, let's create some wild and crazy number and call it E. It does occur in nature quite a bit. Hence the name natural base. So it's a natural base, so when we have our function where we're using E as the base, the function f of x equals e to the x, what do you think this is called? Not just the exponential function, but the, yeah, you guys are good. So when you hear a natural exponential function, you automatically know that the base is E. Unlike our power functions, don't forget that E is my base, so E is the variable or constant. Absolutely. It's a constant, never changing. Our power, our x, that's the one that will be constantly changing. Right? Unlike the power functions, x squared, x cubed, where our constant was the power, now our constant is the base and our power is the variable. So let's look at some of these. Using our calculator, this is what we want. Please be something like this, right? So here, evaluating the f of negative 3. Are we going to expect a large number or small number here? Why? Before you put it in the calculator, why? What does that negative mean? Absolutely. Absolutely. So this has our 1 over e cubed. So definitely, as my negative numbers increase, negative exponents increase, I I should be getting a smaller and smaller number. So where do we wind up here?
2.04.
When x equals 5, so that 148.413, smaller number or larger number? Much smaller, because again, that negative has me 1 over e, and as I get that denominator larger and larger, of course, that overall number is going to get smaller. So my f of negative 7.1, what did you guys get? 8 what? So here we have how many decimal spaces? 6. How many significant digits? 3. I don't know if the book actually uses significant digits, but I may at times, as far as take it to 3 or 4 significant digits, pretty much meaning what? What is a significant digit? Right, we ignore, if I have, after my decimals, to the right of my decimal place, if I have zeros, I ignore the leading zeros. And when I first get to that non-zero, that starts my significant digit. Right? So here we have, starting with this 8, that 8 would be my first significant digit, and then the 2 and the 5 gives me those 3 significant digits. And lastly, dividing at 0.72. Just take a test right now. It's been a while since we used the calculator, so again, definitely make sure that we do know how to utilize that for our quiz on Wednesday. What about using the one-to-one properties for our natural exponential function? Is it any different? No. Now here it's even nicer, right? It's already just written as we have the same base. So what do? Set the exponents equal, absolutely. So we have our 3x plus 2 equals 3. Coming up with x equals 1/3. Once again, we can check, make sure that makes sense. Take that x equals to 1/3. 3 times 1/3 is 1. 1 plus 2, 3. Sure enough, we have that same thing we're looking at. And that took all of 5-10 seconds to check your work. Check it. Make sure that you don't have a negative sign, a positive sign, or something else happen. Over here in part B, again, we set the powers. Equal x squared minus 3 equals 2x. I have an x squared, I have an x. So it says definitely something we want to set equal to 0 and factor. And then we get this impossible factor, so we break out the quadratic formula, right? No? So here, once we factor that quadratic, we get x equals -1 or 3. Question. The big thing with exponential functions, there's quite a bit of very useful applications. A particular one we should all be intimately familiar with, or want to be familiar with, dealing with money. Compound interest. So Anton will take over on this now. So our compound interest, nice formulas we have, especially if you want to compare interest rates on a bank, credit card, home mortgage. You want to find out what's the best value. anything like that. You're loaning money to your friends and you want to find out what's the best interest rate. So, after t years, we use lowercase t. The balance A in an account with principal capital P and annual interest rate lowercase r in decimal form is given by the following formulas. For first one, for n compounding per year. What does that mean for n compounding per year? That's it. It means how many times per year we're actually applying that interest to our principal. So n compounding per year. So we come up with the formula that A is equal to our principal times the quantity 1 plus the interest rate divided by the number of times compounded per year, all raised to the n times t. And for continuous compounding, here we break out our natural exponential function per. Right? So A is equal to P times E, all raised to the RT power. So I have all formulas. This should be the easiest one to remember, right? Yeah. So again, very useful applications using our exponentials with our compound interest. So here we have an example on the day of child's birth. A deposit of $25,000 made into a trust fund that pays 8.25% interest. Determine the balance on the child's 26th birthday. It's compounded quarterly, monthly, and continuously. So, what is that 25,000? This might be. That's the money we started with, our principal. What is the 8.25? I'm sorry? That's my interest rate, but we don't use the 8.25%. We use what?
0.000.
Absolutely, use the decimal form. So I'll move 2 decimals over. And the 26, that's my time, 26 years later. Right? Started at when the child was 0, was born, and we want to find out 26 years later. So, in this particular example here, A for quarterly, what is my N? It is, well, it's just 4. Because again, N represents how many times per year that we're compounding the interest. So if we're compounding the interest quarterly, right, that means 4 times a year, we're adding that 8.25% interest. So we have all our variables using our first formula. So we have our 25,000 for our, right, or we want our A equals, right? 25,000 times 1 plus 0.0825 divided by the number of times compounded, 4, raised to n. Absolutely. So what do we get? What? What did we come up with? 208,942. Anyone not get that? So we get the nice chunk of change, right? Of course, if your parents put that in when you're born, let alone find something that paid 8.25% interest, though. So that's how much we get if we compound it quarterly. If it's compounded monthly, change it to what? Absolutely, my n is now equal to 12. So where do we come up? Do I have to retype that formula? Just select the formula, right, and just go back and change our 4 to 12. Oh. Probably would have been easier just typing in. Giving us 211,989. Then all we did there is use the exact same formula, but instead of having the 4s, replace those with a 12 since it's compounded monthly. What about C? Different formula now, though, right? We're using our A equal P e to the RT, so our 25,000 times e raised to the 0.0825 times 26. 213, I'm sorry. 213,500. You got 5? Be more than $5. Yeah, 5 trillion.
I have 13 zeros.
Did you raise it to the power of 0.0825?
So it's
You probably forgot the decimal.
really 5 million.
Questions on this? Another nice application with the interest, well, I mean that one's with our interest, but another one that you see quite a bit for you science people, dealing with carbon dating or radioactive isotopes half-lives. So here we'll let Q represent the mass of radium, the isotope 226. In grams, whose half-life is just a short one, 1,620. Actually, if you think of like plutonium 240, or no, plutonium 238 or something like that, it's a half-life of like 16,000 or something like that. I mean, some of them are even larger than that. So without sidetracking too much. So with radium 226 isotope in grams, whose half-life is 1,620 years, the quantity of radium present after T years given by the formula. So first part, if we want to determine the initial quantity, how much we started with, what are we letting T equal to?
0.
Absolutely. We're starting off somewhere. We're not starting off at a negative time. We're starting off at T equals 0. So using our calculators in our head, what do we come up with? Sorry? Okay. Just our calculators in our heads. 0 over 1620 is what? 0. Anything to the 0 power is Did we readjust the calibrations there now? Actually, is that true what I just said? Anything raised to the 0 power is 1?
No, it's
Just- So, is that true what I said, that anything to the 0 power is 1? What's the exception? Yeah. So, what about this? Determine the quantity present after 100 years. Right, so we plug it back in the formula, but now that instead of the 0, if you're going to try to use your calculator in your head, good luck. You may be here a while. So using that 16 times 1/2, all raised to the 100 over 1620. I'll wait till everybody has it on the calculator. I do mean everybody. So what do we come up with? 15 point.
15.32290.
So after 100 years, we lost a drastic amount, and almost 6/10 of a gram. Does that answer make sense? That we only lost 6/10 of a gram.
Yes.
Why?
Says about like 16.
Exactly, a half life. So after 1,620 years, we're only going to lose 8 grams. So after 100 years, we should only be losing a small amount. Again, don't just use formulas, equations, and say, here's my answer. Ask yourself when you get that answer, does that make sense? I did 1 + 1 = 4. Don't just say, that's what the calculator told me, so therefore it must be 4. You guys know what I mean, right? So evaluate your answer, does it make sense? Question here. All right, folks, here you go. Stop my recording.